What's going on, everybody? My name is Johnny Bandon, and I'm the CEO and co-founder of Trepa Technologies. In today's video, we're going to continue on our Domain 1.4 lecture by going over PKI components. So now we're going to go over additional things that are used in PKI or that are needed to make PKI secure, have authentication, and non-repudiation. So with that being said, let's go ahead and get started. And I'm going to get my face out of the way, and we can now dive into the lecture. So the first thing we're going to talk about is hashing. So hashing provides this integrity, and when I started learning about cybersecurity and learning encryption, hashing, integrity, all these different components of cybersecurity, this confused me a lot. I didn't understand what it was used for. So I'm going to try to break it down as best as possible. So a hash or hashing is the process of converting an input into a fixed size string of bytes, usually a digest, which appears at random. So just from that definition, probably a little hard to comprehend, right? And what we're essentially saying here is that when you take input, so you take data, you take a message, and you apply a hash function to it, you're not converting that input to ciphertext like encryption. All you're doing is creating a unique digest, unique string of characters that now correlates back to that input. So why is that important? Well, think about digital forensics, where you want to make sure that your evidence is unchanged. Now imagine we have this input hello world. We apply this hashing function against it. We get this unique digest, and we should get that unique digest every single time. So now let's say this is the program that's in question, right? This hello world, probably like we using Python, right, for beginners. And now all of a sudden, let's say that hello world, the O in the hello gets turned into a 0. So let's say we take that input, or someone malicious took this input and converted that O into a 0. Well, now when our digital forensics team wants to examine the input, but now it's been changed in that process of handing it over to digital forensics team, they can verify that by running that hash algorithm against the input again. And if that digest that comes out does not equal, so let's say this is the digest first 3 letters, does not equal the original, then we know it's been changed. So now we can verify the integrity of our data by using a hashing function or a hashing algorithm and comparing the digest, sometimes also known as the checksums. So how can we compare hashing like a Windows machine? So we can check the hash of like this file right here. It says signed PDF in command prompt by using this command. And we can get the digest from the SY0-256 hashing algorithm. PowerShell is the equivalent command. Okay, now let's go over different hashing algorithms. So we have HMAC, which this allows a packet/data to be authenticated and have integrity. So this is using MAC, which is the message authentication, I forgot what the C stands for. Essentially, that provides authentication and using a hash to verify integrity. So, that's right there in front of me, the message authentication code. See, that's how you know I teach from the heart, right? I don't just read these slides. So that uses the MAC, the message authentication code, along with hashing to verify the integrity and to also authenticate messages or data. Then we have the MD5 algorithm, the message digest. This is just a straight up hashing algorithm that is now considered vulnerable due to collisions. So collisions are when the same hash gets produced from 2 separate pieces of data. So that makes it inherently insecure, right? So imagine what collisions are. Let's say you have the word fish and you have the word dog. Well, when you apply the MD5 hashing algorithm, you're supposed to get a unique digest, but imagine that it comes out the same. That is what we call a collision. And now that kind of renders MD5 insecure or really antiquated now. Now we can't use it and we can't trust this hashing algorithm to actually verify integrity. Then we have RIPE-ND. This is another family of hashes, and this is not used in government or commercial use. It's just another hashing algorithm that we may need to know about. So the pretty much the gold standard now of hashing algorithms is SHA, the secure hash algorithm. It's well, I don't know if it's built by NIST, I don't know, but that's what we use in the government. That's the NIST standard, and it comes in different lengths. So obviously the higher the bit key length there, the stronger. So we have up to SHA-512. Okay, now let's go over salting. So let's talk about adding random characters before we actually give a hash, and how that helps us prevent against things like rainbow table attacks, and helps us further verify the authenticity and integrity of data. So let's talk about something in Linux called the shadow file. So in Linux, if you go to the etc folder, shadow, and you type in like cat at your bash shell, that's going to show a list of hashed passwords, okay? So it's going to have a username and then a password associated that's hashed. Now, if we know that a set of characters or a message is always going to have the same unique digest, that's the point. So let's say we take a list of common passwords. So let's just say this is one of them. Password or funky password, or whatever it is, or just let's just say default. Okay, so now we have our list of common passwords, the most vulnerable passwords. And then let's say we run the SHA-256 algorithm against it. Then we're going to get a list of the digests that come from these passwords. So we'll just say this is CF7 DE8 HSK. Obviously, it would be a lot longer, but let's just say for brevity reasons, right? So here's what we'd call our rainbow table. So a list of common passwords and their hashes. So on this rainbow table, we'll say that CF7 equals common password, right? I'm just going to put P here. This equals funky password, and this equals default for D, okay? And again, I'm just brevity reasons. That's why I'm writing it like this. So now let's say somehow we get access to this shadow file on our web server here. So let's say we do cat etc shadow, and from there we can see the list of usernames and passwords. And let's say we have user 1 here, colon, and its hashed password is CF7. Now, to the naked eye, we may not know what that password is. That's just the hash. We're like, okay, I don't know what that is. But now, let's compare it to our rainbow table. So we know, because of our rainbow table, that if we see this hash, that equals regular password. So now it doesn't matter really how strong your hashing algorithm is. That can leave it vulnerable, because now we can kind of reverse it. Say, okay, well, CF7 on my rainbow table equals password. So that means user 1's password is password. So how can we prevent this? We can do something called salting, where we add a random piece of data to the input before the hashing algorithm. So the same salt must be used each time to consistently produce the same hash from the same input, but now it kind of renders those rainbow tables ineffective because this salt is random. It's so random, right? We can't really recreate that in rainbow tables. We'd have to create probably billions of rainbow tables to try to find the equivalent. At that point, what's the point, right? So salting helps us protect against attacks like that, because running the same algorithm against the same input should create the same digest. Okay, now let's talk about digital signatures. So, digital signatures. The whole point of digital signatures is to have what's called authenticity, which means proof of origin, data integrity, of course, because digital signatures use hashing, and something called non-repudiation, which means we can know and verify that this sender is who they say they are and that they sent this message to me. So digital signatures is a cryptographic value that is attached to an electronic document or data or message, and they're used to verify the authenticity of the signer and to ensure that the document has not been altered since it was signed. So essentially, let's say we work in an enterprise and we all use Outlook, and we publish our public keys to, let's say, the global address list, now we can digitally sign and also encrypt, but now we can digitally assign our emails, and within our PKI, we can now verify that. So how are digital signatures created in the concept in this way? So let's actually talk about it. So let's say Amanda here, Amanda's computer, she's the sender, she wants to talk to our receiver, who's going to be on the other slide, okay? And she wants to say, howdy, partner. So this is not encryption, remember, this is just a way to assign a digital signature, to verify authenticity and to have non-repudiation. So the first thing we're going to do is we're going to get the hash of this message. So we're going to get the hash of that message, howdy, partner. So now that we have that hash, so here's that hash, or that message digest of this plain text, the next thing we're going to do is we're going to apply encryption. So now we're going to take Amanda's private key. So for digital signatures to work, so I kind of skipped over this, we need to use asymmetric encryption. We need public and private key pairs. So Amanda is going to create a public key that's going to be published globally that anyone can use, and of course that private key, okay? And remember, those two are mathematically related, so the private key can decrypt the public key's encryption, and the public key can decrypt the private key's encryption, okay? So this is going to come into play. They're both mathematically created. They can encrypt and decrypt each other. So now we're going to, using the private key, encrypt the message digest. Okay, we're going to encrypt the hash, not the original data here. We're encrypting the hash. So once we do that, we create our digital signature. So now that hash is encrypted. See how all the number, the letters have changed? So now we're going to attach the outcome or the result of encrypting the hash of the original plain text. We're going to attach that to our original message here, and that's the digital signature. So here we have our plain text information with this digital signature, which again comes from encrypting the hash of the original message. Now, once the receiver receives that, they're going to be able to view this original message here. It's in plain text, okay? So the first thing that receiver is going to do is going to be like, okay, this was sent from Amanda. So if it's a digital signature, she encrypted it with her private key. So I'm going to decrypt it with her public key that I have. It's available to me. It's the public key. So once we decrypt using the public key of our sender, now we're just left with the hash of that plain text message. Well, we know what the plain text message is, okay? And part of that digital signature, it's going to let you know what hashing algorithm they use. So let's say they use SY0-256. So now that we have that hash, that message digest decrypted, what we're going to do is we're going to take that original message here and run it through the hashing algorithm again. And we're going to look at the results and see, okay, the original plain text message hash is this. Well, I'm going to run the hashing algorithm against that plain text message again. And if they match, then I know that it's authentic, that it hasn't been changed in transit, it has integrity. And since I decrypted it using Amanda's public key, I know that it was from her, because only her public key can decrypt the private key. So now that we have fully verified, we know that we have authenticity, integrity, and non-repudiation. All right, awesome. Now moving on to some more PKI components. So, let's take a breath from digital signatures, right? Probably should have put that at the end of the lecture. That's okay. Let's go over something called key stretching. So key stretching is a technique used to enhance the security of passwords or cryptographic keys. It involves taking a potentially weak key or password and processing it in a way that it becomes more secure against brute force attacks. So here we have PBKDF2. Off the top of my head, I can't not remember what that stands for. In the edit, we'll input it somewhere. I think it's like public key something. Anyways, it uses the SHA hashing algorithm and a salt of at least 64 characters to protect passwords. And we can kind of see another version of that or something similar is bcrypt. So you can always import like the bcrypt library when you're like using Python or when you're coding. Anyways, and this is how we enhance that key. So here we see that hash password, the salt, and then the algorithm here, all attached. And that is key stretching. Okay, some more PKI components we're going to talk about is the blockchain. So a blockchain is a decentralized, distributed ledger that records transactions across many computers in such a way that the registered transactions cannot be altered retroactively, thus kind of ensuring some authenticity, okay? So a blockchain is a secure digital ledger that's supported by a public peer-to-peer network. So the blockchain is supposed to be tamper-proof, right? It's used to protect the integrity, authenticity of data by just a bunch of distributed computers all coming to a consensus that this data is accurate, okay? So the structure, the blockchain is a series of blocks, each containing a list of transactions. Each block is linked to the previous one through cryptographic hashes, forming what's called a chain. So this ledger is not stored in a single location or controlled by a single entity. Instead, it is distributed across a network of computers. So the consensus mechanisms. For a new block to be added to the chain, a consensus must be reached among network participants, which ensures the validity and authenticity of transactions. So this provides us with something called immutability. So once a block is added to the chain, altering it would require changing all subsequent blocks, which is computationally impractical, thus ensuring the security and permanence of the records. So this is just imagine a distributed network of people that all agree to something, and that's their immutability, right? So some use cases like cryptocurrencies, like Bitcoin, that's the technology underpinning Bitcoin is the blockchain, okay? Public ledger. So an open public ledger is a ledger that is openly accessible to anyone. It records transactions or data entries in a way that is transparent, verifiable, and tamper evident. So its relation to the blockchain. So the blockchain is a form of an open public ledger. It provides a mechanism where all transactions are recorded and these records are open for public verification. So the openness and transparency of the blockchain makes it a public ledger where each participant or node in the network can view the entire history of transactions. All right, guys, so that's going to be it for going over PKI components. Now what we're going to do is I'm going to pause the video and then bring up our practice exams where we're going to go over and verify that we did learn something about our PKI components. All right, so here we have our practice exam software up, and if you ever do one of our self-paced courses or come to one of our live virtual trainings, we have over 1,000 practice questions that you have lifetime access to for all certification exams. So this is our software. Now let's go ahead and use it. So what I'm going to do here is read the question out loud, read the answers, take a quick pause or a brief pause. I want you to pause the video, answer for yourself, and then come back. So question 1. What is hashing in cryptography? A, the process of converting a password into plain text. B, a method of encrypting data for secure storage. C, the process of converting data into a fixed size string of characters. Or D, a technique for increasing the speed of database searches. Well, using our process elimination, which you should be doing on the exam, we know for sure that hashing is not increasing the speed. It's cryptography. Nothing in cryptography increases database searches or indexing. A method of encrypting data for secure storage, that's encryption. That provides confidentiality, so it's not going to be B. And then that leads us between A and C. So hashing doesn't convert a password into plain text. It really doesn't even make sense. So we're going to go with C. The process of converting data into a fixed size string of characters. And as you can see here, we have the answer and the explanation as well. Question 2. What is salting in cryptography? A process of adding random data to a password before hashing. Probably going to be that. B, removing sensitive information from data before storing it. C, encrypting data using a symmetric key algorithm. Probably not. That's just, again, encryption. Or D, a method of compressing encrypted data. So we know, because from our learning, that salting helps us protect passwords before the actual hashing. We're going to go with A. And then question 3, I'm going to answer wrong on purpose, just to show you how our software works and how you'll always get the explanation and the correct answer down below. So question 3, what is a digital signature? So it's definitely not A. A digital signature is a cryptographic mechanism that verifies the authenticity of digital messages or documents. So explanation, a digital signature is a cryptographic technique that is used to validate the authenticity and integrity of a message, digital document, or software. All right, I want to thank everyone for viewing. Please feel free to like, share, and of course subscribe. And if you're an active duty, National Guard, or Reserve soldier, click the link in the description below to see how you can use your $4,000 a year to get certified for free. That's right, you can use Army Credentialing Assistance to get free vouchers, free training from any vendor, including yours truly, to get certified. So click that link in the description below if you want to know more, and thank you for viewing.